Now in this lecture we'll answer two questions. In the first question we'll find out the area of this circle that is inside square ABCD, and in the second question we'll find out the area of the green shape that is inside the quarter circle. So we'll start with the first question. In the drawing we have square ABCD. Inside square ABCD we have a circle. We know that this angle TBC equals to 30 degrees. Line segment PD equals to 5 units here. And our mission is to find out the area of this circle. So we'll define the center of this circle as O. We will join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of this circle that we will define as R. We have the radius OP that is drawn to the point of tendency, therefore according to rule number 1, this angle is equal to 90 degrees. Likewise we join points O and Q together by a straight line. Again, here we have point O that is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle that is equal to R, and we have the radius OQ that is drawn to the point of tendency, therefore according to rule number 1 this angle equals to 90 degrees. Okay, and we know that all the angles inside square ABCD are right angles, so here this angle equals to 90 degrees. This angle is equal to 90 degrees. This angle it is also equals to 90 degrees, and finally this angle equals to 90 degrees. So inside quadrilateral AQPO we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees plus the fourth angle plus the size of the fourth angle. In total the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So here 270 degrees plus this angle must be equal to 90 degrees, equals 270 degrees plus 90 degrees, it is 360 degrees. That is the sum of the angles in any quadrilateral. So in order to complete the sum of the angles in this quadrilateral to 360 degrees, this angle must be equal to 90 degrees. So we found out that inside quadrilateral AQPO we have 4 right angles, and therefore quadrilateral AQPO is a rectangle. So I write it down. Quadrilateral AQPO is a rectangle because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side AQ equals to side PO in rectangle AQPO. AQ equals to PO. But we have already found out that PO equals to R, so we can write here that PO equals to R. And from this equation, AQ equals to PO equals to R, we will derive that AQ is also equals to R. Here AQ equals to R. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, so in rectangle AQPO, QO must be equal to AP. QO equals to AP. But we have already found out that QO equals to R, so we can write here that QO equals to R. And for this equation, R equals to QO equals to AP, we will derive that AP is also equals to R. AP equals to R. So I found out that actually quadrilateral AQPO is a square and not a rectangle because of the fact that all of its sides are equal to each other, they are equal to R. So I write it down, quadrilateral AQPO is a square. We know that all the sides of square ABCD are equal to each other. That is to say, side AD equals to side AB in square ABCD. AD equals to AB. I repeat again, side AD equals to side AB in square ABCD. What is the length of side AB? What is the length of side AD? AD equals to R plus 5. And what is the length of side AB? Side AB equals to R plus QB. So in conclusion, we found out that R plus 5 equals to R plus QB. Here we subtract R from this equation and we get that 5 equals to QB. Here QB equals to 5 units. And right here that QB equals to 5 units. In the next step, I will present to you rule number 2 and we will implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point, point P. From the common external point, point P, we have tangent PA and tangent PB. And according to this rule number 2, PA equals to PB. Actually, we can implement rule number 2 in our drawing. Because in our drawing, we will focus on the common external point, point B. From the common external point, point B, we have tangent BQ to the circle and tangent BS. And according to rule number 2, they are equal to each other. That is to say, BQ equals to BS according to rule number 2. But we have already found out that BQ equals to 5 units. So we can write here that BQ equals to 5. And from this equation, 5 equals to BQ equals to BS. We will derive that BS is also equals to 5 units. BS is also equals to 5 units. In the next step, we will join points Q and S together by a straight line. By joining points Q and S, we created here triangle QBS. What is the size of angle QBS? Actually, angle QBS, this angle equals to angle ABC, that is equal to 90 degrees, minus angle TBC, that is equal to 30 degrees. That is to say, angle QBS will be equal to 90 degrees minus 30 degrees, it is 60 degrees. Okay, and inside triangle QSB, side QB equals to side SB, they are both equal to 5 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle, there are equal angles. So those two angles that are located in front of equal sides must be equal to each other. So if this angle is alpha, then this angle must be also equal to alpha because of the fact that those two angles that are located in front of equal sides must be also equal to each other. So both angles are equal to alpha. And what is the sum of those two angles? The sum of those two angles will be equal to 180 degrees minus 60 degrees. That is to say, the sum of those two angles is 120 degrees. So here we found out that alpha plus alpha equals to 120 degrees in triangle QBS. We found out that alpha plus alpha equals to 120 degrees. Alpha plus alpha is 2 alpha, that is equal to 120 degrees. Here we divide this equation by 2 and we get that angle alpha equals to 120 degrees over 2, it is equal to 60 degrees. Okay, we found out that this angle alpha equals to 60 degrees. This angle alpha is also equal to 60 degrees. Therefore, in triangle QBS, all the angles are equal to 60 degrees. Therefore, triangle QBS is an equilateral triangle. So I write it down. Triangle QBS is an equilateral triangle. Why? Because all of its angles are equal to 60 degrees. And we know that in equilateral triangle all the sides are equal to each other. That is to say, in triangle QBS, side QB equals to 5 units, side SB equals to 5 units. Therefore, the missing side QS, must be also equal to 5 units. Here we found out that QS equals to 5 units. In the next step, we join points O and S together by a straight line. Point O is the center of the circle. Point S is the point on the circle itself. Therefore, OS is the radius of the circle that is equal to R. And we have the radius OS that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees. And this angle will be also equal to 90 degrees. So in the next step, I will copy quadrilateral OSBQ in a new page and we will analyze quadrilateral OSBQ. So actually, this is quadrilateral QBOS that I copied from the original drawing. This quadrilateral angle QOS is the missing angle. So what is the value of the missing angle QOS? Angle QOS equals to the sum of the angles in this quadrilateral, that is 360 degrees, minus the sum of the three other angles, minus the sum of 90 degrees plus 90 degrees plus 60 degrees. Okay, so the missing angle QOS equals to 360 degrees minus 90 degrees plus 90 degrees is 180 degrees, and 180 degrees plus 60 degrees is 240 degrees. So we found out that the missing angle QOS equals to 360 degrees minus 240 degrees, it is 120 degrees. So here the missing angle QOS equals to 120 degrees. Here you can write here that angle QOS equals to 120 degrees. In the next step, I will present to you the law of cosines, and we will implement the law of cosines in the green triangle QOS. Okay. So what is the law of cosines? The law of cosines is true in any triangle So if we have triangle ABC that could be any triangle, so this is triangle ABC, the length of side AB is A unit, the length of side AC is B units, and side BC equals to C units in its length, and the angle between side AB and side AC is theta. Then according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. I repeat again, here according to the law of cosines, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Now we will implement the law of cosines in the green triangle QOS. So I will copy triangle QOS in this new page, and we will implement the law of cosines in this triangle. So actually, this is triangle QOS that I copied from the original drawing. QS equals to 5 units, OS equals to R, OQ equals to R, and angle QOS equals to 120 degrees. So according to the law of cosines, we get here that 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. Okay, again 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. 5 squared is 25, and it is equal to R squared plus R squared is 2R squared minus 2 times R is minus 2R squared. Cosine 120 degrees is minus 1 half. So it's substitute cosine 100 degrees by minus 1 half. So here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. Minus times minus is plus, so this expression in total equals to plus r squared. So we find out that 25 equals to 2r squared plus r squared. That is to say, 25 equals to 2r squared plus r squared is 3r squared. Here we will divide this equation by 3 and we get that r squared equals to 25 over 3. And we know that the area of our circle is equal to pi r squared. But we have already found out that r squared equals to 25 over 3, therefore we can substitute r squared in this equation by 25 over 3. We'll do it now. We'll get that the area of our circle equals to pi times 25 over 3. So we found out that the area of our circle equals to 25 pi over 3, or in terms of numbers, it is equal to 26.18 square units. Okay, I'll repeat again, the area of our circle equals to either 25 pi over 3 square units, or in terms of numbers, it is equal to 26.18 square units. We finished with the first question. In the next step, I will present you the second question, and we will solve the second question in 3 different methods. Okay. So in the drawing, we have a quarter circle. Inside the quarter circle, we have a small circle. We know that line segment CD equals to 8 units, angle ACD equals to 90 degrees, and our mission is to find out the value of the area of the green shape, or the area of the green shape. So first of all, we will define the center of this circle, of the small circle, as J. We define the point of tendency of tangent CD with the small circle as E. We define the point of tendency of tangent OB with the small circle as F. We will join points E, J and E together by a straight line. Point J is the center of the small circle, point E is the point of the small circle itself, therefore JE is the radius of the small circle that we will define as R. We have the radius JE that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees. Likewise, we will join points J and F together by a straight line. Point J is the center of the small circle, point F is the point of the small circle itself, therefore JF is the radius of the small circle that is equal to R. We have the radius JF that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees. We know that AOB is a quarter circle, therefore point O is the center of the quarter circle, and angle AOB, this angle equals to 90 degrees. And in addition, we know that OA must be the radius of the quarter circle that we will define as capital R. Okay? So we know that AO is the radius of the quarter circle that is equal to capital R. So AO as a radius must be a straight line. So if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line equals to 180 degrees. So which angles we have at this side of AO at point C? We have this angle that is equal to 90 degrees, plus this angle in total, they must be equal to 180 degrees, according to rule number 3. Therefore, the missing angle, this missing angle must be equal to 90 degrees, In order to complete the sum of the angles on this side of AO at point C to 180 degrees, this angle must be equal to 90 degrees. Then from point J, that is the center of the small circle, we will go perpendicular on CO. So here, this angle equals to 90 degrees, and this angle, it is also equal to 90 degrees according to our construction. We will define the touching point of the perpendicular from point J and CO as T. So inside quadrilateral CETJ, we have 1, 2, 3 right angles. Therefore, the fourth angle, this fourth angle, must be also equal to 90 degrees. Likewise, in quadrilateral TJOF, the lower quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So we actually found out that this angle EJF, equals to 90 degrees plus 90 degrees, it is 180 degrees. Angle EJF equals to 180 degrees. If angle EJF is equal to 180 degrees, it means that angle EJF is a straight line. It is a straight line. Any angle that is equal to 180 degrees, it is a straight line. It means that EJF is a straight line, and if EJF is a straight line, it means that EF is also a straight line. Line segment EF, it is also a straight line. And if line segment EF is a straight line, it means that CEOF, quadrilateral CEOF, is a rectangle. I write it down, quadrilateral CEOF is a rectangle. Why? Because quadrilateral CEOF has 4 right angles. Okay? And we know that the opposite sides of a rectangle are equal to each other. That is to say, CO equals to EF. CO equals to EF in rectangle CEOF. But we have already found out that EF equals to R plus R, that is 2R. And from this equation, CO equals to EF equals to 2R, we will derive that CO is also equals to 2R. Here CO equals to 2R. Okay. In the next step, we'll join points O and D together by a straight line. Point O is the center of the quarter circle. Point D is the point of the quarter circle itself. Therefore, OD is the radius of the quarter circle, that is equal to capital R. In the next step, we will implement the Pythagoras theorem on the right green triangle, triangle OCD. Okay, so according to the Pythagoras theorem, on the right green triangle, triangle OCD, here by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is OD, therefore the square of the hypotenuse is OD squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to CO squared plus CD squared. I'll repeat again. In the right green triangle, triangle OCD, OD squared equals to CO squared plus CD squared. OD equals to capital R, therefore OD square is capital R square. That is equal to CO square. CO equals to 2R, therefore CO square is 2R squared, that is 4R squared, plus CD square. CD equals to 8 according to what is given as the equation, therefore CD square is 8 squared, that is 64. So in conclusion, we found out that according to equation number 1, R square, capital R square equals to 4R square plus 64. Here we subtract 4R square from this equation number 1, and we get that according to equation number 1, capital R square minus 4R square equals to 64. Okay. But what is the area of the green shape? From the drawings it's very easy to see that the area of the green shape equals to the area of the quarter circle minus the area of the small circle. I'll repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. And the area of the quarter circle equals to pi times capital R square over 4. Minus the area of the small circle, that is equal to pi R square. So here we take pi over 4 as a common factor out of those two expressions. So what is left from pi times capital R square over 4 after we took from it pi over 4 as a common factor? What is left is actually capital R square. What is left from minus pi R square after we took from it pi over 4 as a common factor? What is left is actually minus 4R square. Why? Because minus 4R square times pi over 4 equals exactly to minus pi R square. So here we have capital R square minus 4R square, but we have already found out that capital R square minus 4R square according to this equation number 1 equals to 64. Therefore we can substitute capital R square minus 4R square in this equation by 64. We'll do it now and we'll get that this expression equals to pi, in total to pi over 4 times 64. 64 over 4 is 16, so this expression in total equals to 16 pi square units. So the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. We finished with the first method. In the next step I will present to you how to find out the area of this green shape according to the second method. In the second method we use for the things that we only found out in the first method. We have already found out that CO equals to 2R. We have already found out that this angle equals to 90 degrees. We have already found out that this angle is also equals to 90 degrees. And we know that OA is equal to capital R, it is the radius of the quarter circle. Yeah, this is the radius of the small circle. What is the value of line segment AC? From the drawings it is very easy to see that the value of line segment AC equals to AO minus CO. Again, AO minus CO equals to AC. So it is AO minus CO. So that is to say AC equals to AO, that is capital R, minus CO, that is 2R. So in conclusion we found out that AC equals to capital R minus 2R. Capital R minus 2R. So in the next step, we will complete the quarter circle to a circle. So we completed the quarter circle to a circle. We'll extend the radius AO by straight line until it touches the circle. We define the touching point of the extended radius AO and the circle is point T. So here point O is the center of the circle, point T is the point on the circle itself, therefore OT is the radius of the big circle that is equal to capital R. We will extend the straight line DC by straight line until it touches the circle. We'll define the touching point of the extended straight line DC in the circle as M. So here we extended the straight line DC by straight line, and when you extend the straight line by straight line, the result is a straight line. So MD is a straight line. So if we focus on the lower side of the straight line MD, it's point C. Here the sum of the angles must be equal to 180 degrees. So which angles we have here? This angle equals to 90 degrees plus this missing angle. In total, they must be equal to 180 degrees. So the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on the lower side of the straight line MD at point C to 180 degrees. This angle must be equal to 90 degrees. Okay. In the next step, we'll join points M and O together by a straight line. Point O is the center of the big circle, point M is the point on the big circle itself, therefore OM is the radius of the big circle that is equal to capital R. Likewise, we join points O and D together by a straight line. Point O is the center of the big circle, point D is the point on the big circle itself, therefore OD is the radius of the big circle that is equal to capital R. So we have here two right triangles, triangle OCM and the right triangle, triangle OCD. We will prove that those two right triangles can go into each other. So I write it down. We will prove that the right triangle COM is congruent to the right green triangle, triangle OCD. So why those two right triangles congruent to each other? First of all, CO is a common side that belongs to both triangles, so CO equals to itself. CO equals to CO is a common side that belongs to both triangles. In addition, MO equals to OD. Those two sides, they are both the radii of the big circle, therefore they are equal to each other. So OM equals to OD equals to capital R. So we actually proved that those two right triangles congruent to each other by their hypotenuse and one perpendicular. It is enough to prove that those two right triangles congruent to each other. I'll explain you why. Because if, for example, we have a right triangle, triangle ABC, this is the right triangle, triangle ABC. And we know that the perpendicular AB equals to 4 units and the hypotenuse AC equals to 5 units. And we have a second right triangle, triangle DEF. And we know that the perpendicular DE equals to 4 units and the hypotenuse DF equals to 5 units. So in those two right triangles, the perpendicular and the hypotenuse congruent. Therefore, the third side must also congruent. Why? Because according to the Pythagoras theorem, the value of BC is equal to the square root of 5 square minus 4 square. 5 square is 25, minus 4 square is 16, 25 minus 16 is 9, and the square root of 9 is 3. Here also, the value of EF is 5, the square root of 5 square minus 4 square, that is also 3. So we found out that if we have two right triangles that congruent to each other by their perpendicular, one perpendicular and the hypotenuse, then the third side must also congruent. Therefore, we can write down that those two right triangles COM and OCD that congruent by their one perpendicular and the hypotenuse congruent to each other by according to side rule. Why? Because the third side must also congruent, therefore they congruent to each other according to side rule. So I write it down. Triangle, the right triangle, triangle COM congruent to the right triangle, triangle OCD according to side rule. Okay. And for the fact that they can go into each other, we will derive that DC equals to CM. DC equals to CM according to the rule that corresponding sides in congruent triangles are equal to each other. Those two right triangles congruent to each other, therefore the two corresponding sides, that is to say DC and CM, must also congruent. So, but we know that DC equals to 8 units according to what is given as the equation. And from this equation 8 equals to DC equals to CM, we will derive that CM is also equals to 8 units. CM equals to 8 units. And we found out that cm equals to 8 units. In the next step, I will present to you rule number 11 and we will implement rule number 11 in our drawing. According to rule number 11, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 11 in our drawing. Why? Because in our drawing, we have chord AT that intersects with chord MD at point C. Again, chord AT intersects with chord MD at point C. So I write it down. In our drawing, we have chord AT that intersects with chord MD at point C. Point C is the intersection point of chord AT with chord MD. I repeat again. In our drawing, we have chord AT that intersects with chord MD at point C. Therefore, according to rule number 11, we will get that MC times CD equals to AC times CT. Again, MC times CD equals to AC times CT. I write it down according to rule number 11. MC times CD equals to AC times CT. I repeat again, according to rule number 11, we get that MC times CD equals to AC times CT. Okay. MC is 8, CD is 8, MC times CD is 8 times 8, that is 64. And it is equal to AC. AC is capital R minus 2R times CT. What is the value of CT? It is very easy to see from the drawing that CT equals to 2R plus capital R. So according to rule number 11, we found out that 64 equals to capital R minus R times capital R plus 2R. So 64 equals to capital R plus 2R times capital R minus 2R. What is the value of the expression capital R plus 2R times capital R minus 2R? According to the algebraic identity that A plus B times A minus B equals to A squared minus B squared, we will get that the value of the expression capital R plus 2R times capital R minus 2R, it must be equal to A squared minus B squared. In our specific expression, A equals to capital R and B equals to 2R. Therefore, A squared is capital R squared minus B squared is minus 2R squared So in conclusion, we found out that this expression capital R plus 2R times capital R minus 2R equals to capital R squared minus 2R squared. So here 64 equals to capital R squared minus 2R squared is minus 4R squared. So in conclusion, we found out that 64 equals to capital R square minus 4R square. But what is actually the area of the green shape? From the drawing it's very easy to see that the area of the green shape equals to the area of the quarter circle minus the area of the small circle. I repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle, that is pi R square. Then we took pi over 4 as a common factor in the first method, and we found out that inside the brackets we have capital R square minus 4R square. But capital R square minus 4R square, according to this equation, equals to 64. So we can substitute capital R square minus 4R square by 64. We do it now, we get that this expression in total equals to pi over 4 times 64. 64 over 4 is 16, so this expression in total equals to 16 pi. So the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. We finished with the second method. In the next step, I will present to you how to find out the area of this green shape according to the third method. We already found out that CO equals to 2R, AO equals to capital R, and AC equals to capital R minus 2R. And we already found out that this angle equals to 90 degrees. This angle it is also equal to 90 degrees. And also the eye of the small circle is equal to R. In the next step, we will complete the quarter circle to a semicircle. And we will extend the radius AO by straight line until it touches the semicircle. We will define the touching point of the extended radius AO in the semicircle as T. Point O is the center of the semicircle, point T is the point of the semicircle itself, therefore OT is the radius of the semicircle, that is equal to capital R. Okay. We extended the radius AO by a straight line. The radius AO is of course a straight line, and when you extend a straight line by a straight line, the result is a straight line. Therefore AT is a straight line. If AT is a straight line, you can relate to AT as chord inside the semicircle. We have chord AT inside the semicircle that passes through point O, that is the center of the semicircle. Any chord that passes through the center of the circle of the semicircle must be the diameter of the semicircle. Therefore, chord AT that passes from point O, that is the center of the semicircle, it is the diameter of the semicircle. So I write it down that AT is the diameter of the semicircle. In the next step, we'll join points D and T together by a straight line. We'll also join points D and A together by a straight line. So here we created peripheral angle ADT that rests on AT, that is the diameter of the semicircle. And we have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of the circle or semicircle must be equal to 90 degrees. So here we have peripheral angle A and B that rests on AB, that is the diameter of this circle. Therefore, peripheral angle A and B equals to 90 degrees according to this rule, rule number 5. Here we can implement rule number 5 in our drawing, because in our drawing we have peripheral angle ADT that rests on AT, that is the diameter of the semicircle. Therefore, peripheral angle ADT equals to 90 degrees according to rule number 5. Okay. Peripheral angle ADT equals to 90 degrees. Okay. In the next step, we will define angle ATD as alpha. We will define angle TAD as beta. So inside the right triangle ADT, this right triangle, angle ADT equals to 90 degrees. Therefore, the sum of the other two angles must be also equal to 90 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Okay? That is to say, alpha plus beta equals to 90 degrees. Here we subtract alpha from this equation and we get that beta equals to 90 degrees minus alpha. We subtract alpha from this equation, we subtract beta from this equation and we get that alpha equals to 90 degrees minus beta. We focus on the right green triangle, triangle ACD, this right green triangle. This angle equals to 90 degrees. This angle equals to beta, therefore the third angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. It is the sum of the angles in any triangle. So this angle must be equal to 90 degrees minus beta, but we have already found out that 90 degrees minus beta equals to alpha. So here we can write down that this angle equals to alpha. Likewise, we will focus on the right triangle, triangle CDT. On the right triangle, triangle CDT, this angle equals to 90 degrees. This angle equals to alpha, therefore the missing angle must be equal to 90 degrees minus alpha, but we have already found out that 90 degrees minus alpha equals to beta. So we can write here that this angle equals to beta. In the next step, we will prove that the right green triangle, triangle ACD, is similar to the right green triangle, triangle CDT. So why those two right triangles are similar to each other? I write it down. We will prove that the right green triangle, triangle ACD, is similar to the right triangle, triangle CDT. Why those two right triangles are similar to each other? First of all, those two angles, they are both equal to alpha, therefore they are equal to each other. That is to say, angle ADC is equal to this angle, that is actually angle CTD. In addition, those two angles, they are both equal to beta, therefore they are equal to each other. So this angle is angle CAD. That is equal to this angle, that is actually angle CDT. And finally, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So this angle is angle ACD. That is equal to this angle, that is angle DCT. So we actually prove that those two right triangles are similar to each other according to angle similarity rule. So I write it down. The right green triangle, triangle ACD, is similar to the right green triangle, triangle CDT, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We will derive that AC in the right triangle ACD over CD in the right triangle CDT equals to CD over CT. I repeat again, we conclude that AC over CD equals to CD over CT. AC equals to capital R minus 2R over CD. CD equals to 8 units according to what is given as the equation, and it is equal to CD over CT. And what is the value of CT? CT equals to capital R plus 2R. So in conclusion, we found out that according to equation number 1, capital R minus 2R over 8 equals to 8 over capital R plus 2R. Here we cross multiply this equation number 1, and you get that according to equation number 1, 8 times 8 is 64, and it is equal to capital R plus 2R times capital R minus 2R. So 64 equals to, we have already found out that capital R plus 2R times capital R minus 2R equals to capital R square minus 4R square. So we actually found out that according to equation number 1, 64 equals to capital R square minus 4R square. What is the area of the green shape? The area of the green shape is actually equals to the area of the quarter circle minus the area of the small circle. I repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle, that is pi r square. Then we took pi over 4 as a common factor out of those two expressions. So inside the brackets we left only with capital R square minus 4r square. But we have already found out that capital R square minus 4r square equals to 64. So we can substitute capital R square minus 4r square in this equation by 64. We'll do it now. We'll get that this expression in total equals to pi over 4 times 64. 64 over 4 is 16, so this expression in total equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, so in terms of numbers it is equal to 50.265 square units. We finished with the third method and the second question. In the next step I will summarize the lecture. We'll start with the first question, of course. In the drawing we have square ABCD. Inside square ABCD we have a circle. We know that angle CBT equals to 30 degrees. Line segment PD equals to 5 units, and our mission is to find out the area of this circle. We define the center of this circle as O. We have the radius OP that is drawn to the point of tendency, therefore this angle equals to 90 degrees. Likewise, we have the radius OQ that is drawn to the point of tendency, therefore this angle is also equals to 90 degrees according to rule number 1. We know that all the angles inside the square are right angles, so in square ABCD all the angles are right angles. So those 4 angles are all right angles inside square ABCD. So inside quadrilateral AQPO we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, therefore the fourth angle must be also equal to 90 degrees. Therefore in quadrilateral AQPO we have 4 right angles, and therefore quadrilateral AQPO is a rectangle. You know that the opposite sides of a rectangle are equal to each other, that is to say AQ equals to PO. But we have already found out that PO equals to R, and from this equation AQ equals to PO equals to R, we will derive that AQ is also equals to R. Here AQ equals to R. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that QO equals to AP. But we have already found out that QO equals to R, and from this equation R equals to QO equals to AP, we will derive that AP is also equals to R. AP equals to R. So we found out that quadrilateral AQPO is not a rectangle but a square because of the fact that all of its sides are equal to each other, they are equal to R. We know that in square ABCD all the sides are equal to each other, that is to say side AD equals to side AB. In square ABCD, side AD equals to side AB. Side AD equals to side AB. Side AD equals to R plus 5. Side AB equals to R plus QB. Therefore, we found out that R plus 5 equals to R plus QB. We subtracted R from this equation. We found out that QB equals to 5. Here, QB equals to 5. Then I presented to you rule number 2, and we implemented rule number 2 in our drawing. According to rule number 2, the lengths of 2 tangents from a common external point to a circle are equal. We have the common external point, point P. From the common external point, point P, we have 2 tangents to the circle, tangent PA and tangent PB. And according to this rule number 2, PA equals to PB. We can implement rule number 2 in our drawing, because in our drawing we have the common external point, point B. From the common external point, point B, we have 2 tangents to the circle, tangent BQ and tangent BS. And according to rule number 2, they are equal to each other. Here, BQ equals to BS according to rule number 2, but we have already found out that BQ equals to 5. So from this equation 5 equals to BQ equals to BS, we derive that BS is also equals to 5. Here, BS is also equals to 5. Then we join point Q and S together by straight line. By joining points Q and S by straight line, we created here triangle QSB. What is the size of angle QBS? The size of this angle will be equal to the size of angle ABC minus the size of angle TBC. Again, ABC minus TBC will be equal to this angle. ABC is 90 degrees, TBC is 30 degrees, therefore this angle must be equal to 90 degrees minus 30 degrees, that is 60 degrees. Then in triangle QSB, those two sides are both equal to 5 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle, they are equal angles. So those two angles that are located in front of equal sides must be equal to each other. So if this angle is alpha, this angle must be also equal to alpha because of the fact that those two angles that are located in front of equal sides must be equal to each other. So those two angles, they are both equal to alpha. And what is the sum of those two angles? The sum of those two angles must be equal to 180 degrees minus 60 degrees. 180 degrees minus 60 degrees, it is 120 degrees. So we found out that alpha plus alpha equals to 120 degrees. Here alpha plus alpha equals to 120 degrees in triangle QBS. Alpha plus alpha is to alpha, that is equal to 120 degrees. We divided this equation by 2 and found out that angular alpha equals to 120 degrees over 2 is 60 degrees. So we found out that those two angles are both equal to 60 degrees. Therefore, in triangle QSB, we have three angles that are all equal to 60 degrees. Therefore, triangle QSB is an equilateral triangle. And we know that all the sides of equilateral triangle are equal to each other. That is to say, side QB equals to side BS equals to side SQ. So QB equals to 5, BS equals to 5. Therefore, the missing side QS must be also equal to 5. Okay? Then we join points O and S together by a straight line. Point O is the center of the circle. Point S is the point on the circle itself. Therefore, OS is the radius of this circle that is equal to R. We have the radius OS that is drawn to the point of tendency. Therefore, according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. Then incorporate quadrilateral QBOS in the new page and we analyze quadrilateral QBOS. This is quadrilateral QBOS that I copied from the original drawing. Those two angles are both right angles. This angle equals to 60 degrees and this is the missing angle. Angle QOS is the missing angle. What is the size of this angle? The size of the missing angle will be equal to the sum of the angles in quadrilateral QBOS, that is 360 degrees, minus the sum of the three other angles. That is to say, it is equal to 360 degrees minus the sum of three angles, that is 90 degrees plus 90 degrees plus 60 degrees. That is to say, the missing angle QOS equals to 360 degrees and 90 degrees plus 90 degrees plus 60 degrees is 240 degrees. So in conclusion, we found out that the missing angle QOS equals to 360 degrees minus 240 degrees, that is 120 degrees. So we found out that the missing angle equals to 120 degrees. So this is the missing angle that is equal to 120 degrees. Then I presented to you the law of cosines and we implemented the law of cosines in this green triangle, triangle QOS. What is the law of cosines? The law of cosines is true in any triangle. So if we have here triangle ABC that could be any triangle, the length of side AB is A units, the length of side AC is B units, and the length of side BC is C units, and the angle between side AB and side AC is theta. Then according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Okay, then we implemented the law of cosines in triangle QOS. QO equals to R, OS equals to R, QS equals to 5, and angle QOS equals to 180 degrees. So according to the law of cosines, here 5 square equals to R square plus R square minus 2 times R times cosine 120 degrees. Again, 5 square equals to R square plus R square minus 2 times R times cosine 120 degrees. 5 square is 25, R square plus R square is 2R square, minus 2R times R is minus 2R square, times cosine 120 degrees. Cosine 120 degrees equals to minus 1 half. So we substitute cosine 120 degrees by minus 1 half. We have 2 in the numerator and 2 in the denominator. So 2 will get cancelled. Minus times minus is plus. So total, this expression equals to plus r squared. That is to say, 25 equals to 2r squared plus r squared. 2r squared plus r squared is 3r squared. So, in conclusion, found out that 25 equals to 3r squared. We divided this equation by 3 and found out that r squared equals to 25 over 3. What is the area of our circle? The area of our circle equals to pi r squared. But we have already found out that r squared equals to 25 over 3. Therefore, we can substitute r squared in this equation by 25 over 3. We did it, and we got that the area of our circle equals to pi times 25 over 3. Or the area of our circle equals to either 25 pi over 3 square units, or in terms of numbers, it is equal to 26.18 square units. We finished with the first question, then I presented to you the second question, and we solved the second question in 3 different methods. So, here, in the drawing we have a quarter circle. Inside the quarter circle we have a small circle. We know that line segment CD equals to 8 units, angle ACD equals to 90 degrees. Our mission is to find out the area of the green shape. We define the center of the small circle as J. Here we have the radius JE that is drawn to the point of tendency, therefore this angle equals to 90 degrees. We have the radius JF that is drawn to the point of tendency, therefore this angle equals to 90 degrees. We know that A or B is a quarter circle, therefore point O is the center of the quarter circle, and this angle equals to 90 degrees. And in addition, AO is the radius of the quarter circle, that is equal to capital R according to our definition. The radius of the small circle equals to R. Then from point J, we draw perpendicular on CO. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our definition. We define the touching point of the perpendicular from point J in CO as T. So in quadrilateral CEJT, in the upper quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Likewise, in the lower small quadrilateral TJOF, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So we found out that angle EJF equals to 90 degrees plus 90 degrees, it is 180 degrees. So angle EJF equals to 180 degrees, therefore angle EJF is a straight line. So if angle EJF is a straight line, then EJF is a straight line, and then EF is also a straight line. So if line segment EF is a straight line, it means that quadrilateral CEOF is a rectangle. Quadrilateral CEOF is a rectangle. Why? Because it has 4 right angles. And we know that the opposite sides of rectangle are equal to each other. That is to say, CO equals to EF. But we have already found out that EF equals to R plus R, that is 2R. So from this equation, CO equals to EF equals to 2R, we will derive that CO is also equals to 2R. Then we join points O and D together by a straight line. Point O is the center of the quarter circle. Point D is the point of the quarter circle itself, therefore OD is the radius of the quarter circle, that is equal to capital R according to our definition. Then we implemented the Pythagoras theorem on the right green triangle, triangle COD. In the right green triangle, triangle COD, we get that OD square equal to OC square plus CD square. I repeat again, the right triangle, triangle CD by PT is by Pythagoras theorem, OD square equals to CO square plus CD square. OD is R, so OD square is OD is capital R, therefore OD square is capital R square, that is equal to CO square. CO is 2R, therefore CO square is 2R square, that is 4R square, plus CD square. CD is 8, so CD square is 8 square, that is 64. So in conclusion, we found out that according to equation number 1, capital R square equals to 4R square plus 64. Then we subtracted 4R square from this equation, and we found out that capital R square minus 4R square equals to 64 according to equation number 1. But what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. I repeat again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle is pi times capital R over 4. The area of the small circle is pi r square. We took pi over 4 as a common factor out of those two expressions, so what is left inside the bracket after we took from pi times capital R square over 4 common factor pi over 4, what is left is actually capital R square. What is left from minus pi R square after we took from it pi over 4 is a common factor. What is left is minus 4R square. Why? Because minus 4R square times pi over 4 equals exactly to minus pi R square. Minus pi R square. So we found out that the area of the green shape equals to pi over 4 times capital R square minus 4R square. But we already found out here that capital R square minus 4R square equals to 64. Therefore, we can substitute capital R square minus 4R square by 64. We did it when we got that this, the area of the green shape, this expression equals to pi over 4 times 64. 64 over 4 is 16. So in total, this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, so in terms of numbers, it is equal to 50.265 square units. We finish with the first method, then I presented to you how to find out the area of the green shape according to the second method. In the second method, we use all the things that we have already found out in the first method. We have already found out in the first method that CO equals to 2R. We have already found out that AO equals to capital R, and this again equals to 90 degrees. What is the value of AC? The value of AC is AO minus CO. Again, AO minus CO equals to AC. So AC equals to AO minus CO. AO is capital R and CO is 2R. So in conclusion, we found out that AC equals to capital R minus 2R. Then we completed the quarter circle to a circle. We extended the radius AO by a straight line until it touches the circle at point P. At point T. Point O is the center of the big circle. Point T is the point of the big circle itself. Therefore, OT is the radius of the big circle that is equal to capital R. Then we extended the straight line DC by a straight line until it touches the circle at point M. When we extended the straight line DC by a straight line, the result must be a straight line. So DM must be a straight line. So if we focus on the lower side of the straight line DM at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have here? This angle equals to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees according to rule number 3. So the missing angle here must be equal to 90 degrees in order to complete the sum of the angles in the lower side of the straight line MD at point C to 180 degrees. This angle must be also equal to 90 degrees. So we created here two right angles, triangle DCO and triangle MCO. Then we proved that those two right triangles can go into each other. Why they can go into each other? First of all, CO is a common side that belongs to both triangles. So CO equals to itself. And then we have DO equals to OM. They are both the radii of the big circle, therefore they are equal to each other. Here we proved that the perpendicular CO and the hypotenuse DO and OB, they can go in those two right triangles. Therefore, it is enough in order to prove that those two right triangles can go into each other. Why? Because if, for example, we have two right triangles, triangle ABC and triangle DEF, those two right triangles can go into each other by their hypotenuse and one perpendicular. If we have hypotenuse and perpendicular that can go in two right triangles, then the third side must also congruent. Why? Because according to the Pythagoras theorem, in this example, the third side, the value of the third side BC here is the square root of 5 squared minus 4 squared, this is 3. So we can say that if we have hypotenuse and one perpendicular that congruent, then the third side must also congruent. Here BC equals to EF equals to 3. Therefore, those two right triangles must congruent to each other according to side rule. The right triangle COM can go into each other according to side rule. From the fact that they can go into each other, we derive that DC equals to CM according to the rule that corresponding sides of congruent triangles are equal to each other. Those two triangles can go into each other, therefore the corresponding sides, that is to say CD and CM, must be also equal to each other. But it is given as the equation that DC equals to 8. And from this equation 8 equals to DC equals to CM, we derive that CM is also equals to 8 units. Here CM equals to 8 units. Then I presented to you rule number 11, and we implemented rule number 11 in our drawing. What is rule number 11? According to rule number 11, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 11 in our drawing, because in our drawing we have chord AT that intersects with chord MD at point C, and then chord AT intersects with chord MD at point C. Therefore, here, I repeat again, in our drawing we have chord AT that intersects with chord MD at point C. Therefore, according to rule number 11, we will get that MC times CD equals to AC times CT. Again, MC times CD equals to AC times CT. I'll repeat again. According to rule number 11, we get that MC times CD equals to AC times CT. MC is 8, CD is 8, so MC times CD is 8 times 8 is 64. AC equals to capital R minus 2R, and CT equals to capital R plus 2R. Therefore, again, AC equals to capital R minus 2R, and CT equals to capital R plus 2R. So in conclusion, we found out that 64 equals to capital R minus 2R times capital R plus 2R. What is the value of this expression? According to the algebraic identity that A plus B times A minus B equals to A squared minus B squared, we will get that capital R squared times capital R plus 2R times capital R minus 2R will be equal to, here, A equals to capital R and B equals to 2R. Therefore, A squared minus B squared is capital R squared minus 2R squared. That is to say, 64 equals to capital R squared minus 2R squared minus 4R squared. So in conclusion, we found out that 64 equals to capital R squared minus 4R squared. But what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. We already found out that the area of the quarter circle equals to pi times capital R squared over 4. The area of the small circle equals to pi R squared. Then we took pi over 4 as a common factor out of those two expressions. So inside the brackets we left only with capital R squared minus 4R squared. But we have already found out that capital R squared minus 4R squared equals to 64. Therefore, we can substitute capital R squared minus 4R squared by 64. We did it, and we got that this expression in total equals to pi over 4 times 64. 64 over 4 is 16. So this expression in total equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. We finished with the second method. Then I presented to you how to find out the area of the green shape according to the third method. In the third method, we use the following things that we already found out in the previous methods. We've already found out that CO equals to 2R. We've already found out that AO equals to capital R, and we have already found out in the second method that AC equals to capital R minus 2R. This angle equals to 90 degrees, and this angle equals to 90 degrees, according to what we have already found out. Then we extended the quarter circle to a semicircle. Then we extended the radius. We completed the quarter circle to a semicircle, and we extended the radius AO by a straight line until it touches the semicircle at point T. Point O is the center of the semicircle. Point T is the point of the semicircle itself. Therefore, OT is equal to capital R, that is the radius of the semicircle. We extended the radius AO, that is a straight line, by a straight line. When you extend a straight line by a straight line, the result is a straight line. So AT is a straight line. If AT is a straight line, we can see AT as a chord inside a semicircle. Any chord that passes through the center of the semicircle must be equal to the diameter, must be the diameter of the semicircle. Chord AT passes through point O, that is the center of the semicircle, therefore chord AT is the diameter of the semicircle. AT is the diameter of the semicircle. Then we join point Z and T together by a straight line. We join point Z and A together by a straight line. In this way, we created peripheral angle ADT. and we have peripheral angle ADT rests on 18, this is the diameter of the semicircle. And we have rule number 5. According to rule number 5, any peripheral angle that rests on the diameter of the circle or semicircle must be equal to 90 degrees. We have peripheral angle A and B that rests on AB, that is the diameter of the circle, therefore peripheral angle A and B equals to 90 degrees according to this rule number 5. We can implement rule number 5 in our drawing because we have here peripheral angle ADT that rests on 80, that is the diameter of the semicircle, therefore peripheral angle ADT must be equal to 90 degrees according to rule number 5. Then we define angle ATD as alpha, we define angle TAD as beta. So in the right triangle, triangle ADT, this is the right triangle. In this right triangle, this angle equals to 90 degrees. Therefore, the rest, other two angles, must be also equal to 90 degrees. That is to say, alpha plus beta equals to 90 degrees. We subtracted alpha from this equation, we found out that beta equals to 90 degrees minus alpha. Then we subtracted beta from this equation and we found out that alpha equals to 90 degrees minus beta. Then in the right triangle ADC, this angle equals to beta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees, that is the sum of the angles in any triangle. So this angle must be equal to 90 degrees minus beta, but we already found out that 90 degrees minus beta equals to alpha. So we can substitute 90 degrees minus beta here by alpha. Likewise, in the right triangle CDT, this angle equals to alpha. This angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus alpha. But we already found out that 90 degrees minus alpha equals to beta, so we can substitute 90 degrees minus alpha here by beta. Then we prove that the right triangle, triangle ADC, is similar to the right triangle, triangle CDT. Why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles they are both equal to beta, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So we found out that those two right triangles are similar to each other according to angle similarity rule. And for the fact that they are similar to each other, we derive that AC over CD equals to CD over CT. I repeat again, AC over CD equals to CD over CT. Okay, AC equals to capital R minus 2R, CD equals to 8, and CT equals to capital R plus 2R. So in conclusion, we found out that according to equation number 1, capital R plus 2R over 8 equals to 8 over capital R plus 2R. Here we cross multiply this equation, equation number 1, and we found out that 8 times 8 is 64. 64 equals to capital R plus 2R times capital R minus 2R. But we have already found out that capital R plus 2R times capital R minus 2R equals to capital R square minus 4R square. So in conclusion, we found out that according to equation number 1, 64 equals to capital R square minus 4R square. And what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the minus the area of the small circle. We have already found out that the area of the quarter circle equals to pi times capital R square over 4. We have already found out that the area of the small circle is pi R square. We took pi over 4 as a common factor of those two expressions. Inside the brackets, we left only with capital R square minus 4R square. But we have already found out that capital R square minus 4R square, according to equation number 1, equals to 64. So we can substitute capital R square minus 4R square by 64 in this equation. We did it, and we got that this expression equals to pi over 4 times 64. 64 over 4 is 16, so this expression in total equals to 16 pi. So in conclusion, we found out that the area of the green shape equals to either 16 pi square units, so in terms of numbers, it is equal to 50.265 units. So in all three methods, we found out that the area of this green shape equals to either 16 pi square units, so in terms of numbers, it is equal to 50.265 square units. Okay, thank you very much.